do this. If I have both of those in an aqueous solution, let's first look at hydrofluoric acid. Is hydrofluoric acid strong or is it weak?
Weak.
It's weak. Okay, so which means that partially it's going to dissociate into hydrogen and fluoride ions, which is why we need to have the double arrow. Anytime it's weak, you need a double arrow because you don't have 100% dissociation. Now, all of these are aqueous. And if I have that solution of hydrofluoric acid and I take sodium fluoride, solid sodium fluoride, and I dump it into a solution, sodium fluoride is a salt, and so it will also dissociate. Now it's just going to completely dissociate into sodium ions, and this would be like solid sodium fluoride, into aqueous sodium ions and aqueous fluoride ions. Now, before we move on, let me just address something that is a common mistake that people make when you're dealing with this whole common ion thing. You see the problem, and the question is going to say, you know, we've got hydrofluoric acid and we add sodium fluoride to it. And so because of that word add, people just automatically go, okay, I've got hydrofluoric acid plus sodium fluoride. That's my reaction, then I'm going to see what happens. Okay? That is not okay. And why that's not okay for you to write it that way, and we're going to look at how to write it properly in just a minute. Why you can't write it that way is because if you have hydrofluoric acid, which is weak, and fluoride ions, the hydrofluoric acid, that's of course the acid. The fluoride ions are the conjugate base of hydrofluoric acid. Do acids and conjugate bases of that acid go on the same side of the reaction? No, they do not. They go on opposite sides of the arrow. And so those two things need to be shown on the opposite sides. So these are conjugate acid-base pairs. So they're partners, basically. And those partners cannot go on the same side. They have to go on opposite sides. So let's write this, and then I'll show you what the reaction does look like. Did they do it?
Yeah.
Oh, yay. That was fast. Thank you. That's it. Oh, no, that's not it. But I'll give it to you. The actual reaction, when you have a solution of hydrofluoric acid and you add sodium fluoride to it, is actually no different than the reaction that you write out just for the dissociation of hydrofluoric acid. And so when you write it out, it's just HF into hydrogen ions, fluoride ions. Now the only difference here is that normally, if we're dealing with just hydrofluoric acid, we have a starting concentration here, and everything else over here is 0. But when you have this common ion added in, which is the fluoride ion here, you just have an initial concentration as part of your ICE table for this fluoride ion. And then this is actually just 0. These aren't zeros, these are actual numbers. So you're going to have numbers that you start with. So now you have, instead of plugging in a 0 here, you have a number to start with. And so this is the reaction still that you write out, even though you're adding sodium fluoride to it. Okay, now what happens when you do that is that fluoride ion from the sodium fluoride comes in here and fills in on the product side of the reaction, causing it to kind of shift to the left a little bit because I'm increasing the concentration of the fluoride ion. And not only does that happen, it also kind of makes the forward reaction stop happening as much, so it prevents the forward reaction from taking place and prevents more hydrogen ions from being formed. And so there's less hydrogen ions produced, there's less dissociation whenever you have a common ion to start with, and therefore affecting the pH because you have less hydrogen ions. Okay, so you can write this down. I was going to have you do it separately. Huh? Yeah. I was going to make you go through and do this. This was pretty much a question on your test from Wednesday. From chapter 14, you guys went through and you calculated the percent dissociation of weak acids. You had Ka values, you did the ICE table, you solved for X, and X was the concentration of hydrogen, and then you negative log it and you find the pH. Oh, what do you do to find the percent dissociation after you go through and you solve for X? And that's the concentration of hydrogen ions. What do you do with that number? Divide it by the initial concentration, right? Which in this case is your 0.10 molar. And then you figure out the percent. Now, I was going to make you redo it, but I'm not going to. If you went through and you did that calculation and you solved for the percent dissociation for just acetic acid only, there's nothing else but acetic acid, the percent dissociation is 1.3%. So now we're going to go through and we're going to calculate the percent dissociation if we have the common ion and then compare the two and how that affects the hydrogen ion production. As a side note of acetic acid, we write it like this a lot because we can see that it's acidic. We have the positive hydrogen ion and the negative acetate ion. You may also see it written like this, CH3COOH. You have to be able to recognize that as the same thing. So I mean, if you count it up, you've got 4 hydrogens, you've got 2 carbons, you've got 2 oxygens. The reason why they write it this way sometimes is more of a structural clue as to how the actual molecule looks. So if you were to draw out the Lewis structure for it, you have this CH3 kind of over here on one side, and then it's attached to something where you have the carbon, and then the 2 oxygens, and then the last hydrogen. And so they write it that way because it deals more with, with the structure of the formula. Who's in AP Bio? Anybody? Do you know what this is? This is carboxyl group, which makes acetic acid a carboxylic acid. We're going to talk about that more when we talk about organic chemistry, but since I'm talking about it now, there you go. All right, now let's calculate the percent dissociation when we have 0.1 molar acetic acid and 0.1 molar sodium acetate added to that solution. All right, there's nothing super tricky here. I'm going to write out my dissociation equation for acetic acid, hydrogen ions, acetate ions. My starting concentration is 0.1 molar here, 0.1 molar here, 0 there. Now if you go through and you set up your ice table, you get 0.10 plus x, x, and 0.10 minus x. You would also be given the Ka values for all of these things anytime you would need it. You probably know the Ka value for acetic acid by heart because you use it so many times. Does anybody know? 1.8 times 10 to the negative 5. That's going to equal products over reactants. So 0.10 plus x times x over 0.10 minus x. Ka is super small. What can I do with those x's that I have circled in red? Cancel out. Make them 0. Okay, because it's not going to affect it very much. I can't cancel out this x. So you end up with 1.85 equals 0.1x over 0.1. Without your calculators, x equals what number? Here you go. 1.8 times 10, yeah, very close. 1.8 times 10 to the negative 5. Now, I want to figure out the percent dissociation. So to do that, I'm going to take that 1.8 times 10 to the negative 5, divide it by the initial concentration of 1 molar, times 100 to give me percent. You get 0.018%. If I compare that number with the number that we calculated up here, it is, of course, much smaller. 0.018 is much smaller than 1.3%. So if you just have acetic acid by itself, you have 1.3% dissociation. And if you add that common ion of acetate and you have a starting initial concentration here, it prevents the dissociation of the weak acid. So you get less hydrogen ions. You only get 0.018%. And so that's going to affect the pH of the solution. Okay, the more common ion you have, the less dissociation of the weak acid. So if this number was bigger, the bigger this number is right here, the smaller your percent dissociation is. That's just getting us warmed up. Are you warmed up? Are you ready? Okay, now let's talk about what buffers are. Oh, I'll give you a break in a minute. I will give you an in-between the notes break today because it's necessary. So, but not yet, not yet. We have to talk about buffers first. And then I am going to give you your favorite equation of the entire year.
I feel like this is true.
No, it's my favorite equation.
Yeah, there you go. I still feel like this is not fun.
Second period was laughing at me because I was like so giddy about this. Somebody has to be.
I'm scared.
Yes, I know it's like Hess's Law. Love. No, you will.
Do you like
Is this all my
Yeah.
Hess's
I
Law?
thought you liked it.
Yeah, she did the example, and I did it on my own. I was like, this is hard. I don't like it anymore.
There was something where you're like, I seriously really like
It was, no, it was, chapter like 9 and 10, like, what's it?
solutions.
No, it was.
When you built the
When you build the
Oh,
model.
yeah.
Oh, yeah.
I was
Yeah.
good at that. I was like,
Oh,
Yeah.
that's chapter 8,
Structures.
Vesper.
The
Yeah.
non-pipe
I also love
fuzzy
that.
sticks.
Okay, first thing up here is just the definition of what a buffer is, okay? We've been talking about how chapter 15 is about buffers. And so what you need to know is that all a buffer is it's a solution. So it's an aqueous solution and it's got a bunch of stuff just floating around in it, a lot of ions and a lot of things going on in there. It is specifically a solution that resists a change in pH. And what that means is that the combination of stuff in a buffer acts in a way that if you add something super acidic to it, that the pH doesn't change very much. Or if you add something that's super basic to the buffer solution, the pH doesn't change very much. It resists that change because of everything that's in there. And we're going to show how that works in a little bit. Does anybody know of any solutions, important solutions that are buffers? No. Your blood. Your blood is a buffered solution, and it better be, because every time you drink a soda, you don't want your blood pH to like go down and become super acidic all of a sudden. Yes.
I thought it was a buffer because of your kidneys, though.
And because of everything else that has to go on. So I would just say any kind of change in pH that would result, it doesn't affect the pH of your blood. It has to stay pretty much the same. There's not a lot of room for change. There is like a phosphate buffered solution like within your cells that keeps the pH balanced inside your cells as well. Okay, now requirements in order to identify if something is a buffer or not. It has to have a combination of two things: a weak acid and it's a significant quantity of its conjugate base. So those would be like acidic buffers. And then you can have a weak base and its conjugate acid partner. So one or the other you have to have in order for it to be a buffer. Now, when I say a significant quantity of the partner, what does that mean? The significant quantity just means within a factor of 10. It's actually a wide range for it to be enough to actually buffer the solution. So if the concentration of your weak acid is 1.0 molar, then that means for the conjugate base, you need to have a concentration anywhere from, so divide it by 10, anywhere from 0.1 molar to all the way up to 10 times that, 10 molar. So if you have anything within that, as far as the concentration of the conjugate base, then it's considered to be a buffered solution and will resist the change in pH. An ideal buffer has the same concentration of both. All right. So, first question. You need to be able to calculate the pH of a buffered solution. All right, I've got 50 milliliters of 0.5 molar sodium acetate solution. It's mixed with 25 milliliters of 0.25 molar acetic acid solution. What's the resulting pH of the buffered solution? So whenever you have a buffer where you have these common ions, all I'm doing is writing out the dissociation reaction for acetic acid. Okay, so we've done this lots of times. And in order to figure out the pH, I'm looking for the hydrogen ion concentration. So I'm going to set up an ice table. Now let's see. The initial concentration of acetic acid is 0.083 molar. And the initial concentration of the acetate ion is 0.33 molar. Where did I get those numbers from? I don't see those numbers anywhere in the question. So I mean, I had to do something, and you would have to do something. But we've done it before. Where did I get them? M1V1, M2V2. Okay, I'm combining two solutions. So for each one of those things, I plugged in the initial molarity, the initial volume, and then divided it by the volume of the combined volume, which would be 75 milliliters, to get what the molarity is of those solutions. So that's where those numbers came from. Now, I didn't want to spend a ton of time on that. So then, once you set up your ice table, then everything else is the same. So I have 0.33 plus X, and I have X, 0.083 minus X. Okay, now I'm not going to spend a lot of time solving for X. Okay, we've done that repeatedly. So I solve for X, that equals my hydrogen ion concentration. They would give you the Ka value, 1.8 times 10 to the negative 5. So you get 4.5 times 10 to the negative 6 as your concentration for hydrogen. What do I do with that number in order to get the pH? Negative log it, 5.35. Zach, did you have a question?
Yeah. How did you find the M1V1 of just C2H2O2 minus?
It would be the same as if I found the M2 for this entire thing. Because for every 1 mole of that, I have 1 mole of that. So since the ratio is 1 to 1, really what you calculate when you do M1V1, M2V2 is the concentration of that whole thing. But it's the concentration of just the sodium ions and the concentration of just the acetate ions. All right, so then the pH of that buffered solution is 5.35. Okay, so that's the same as normal. Now, I want to talk about something that's a little bit different that's going to help us a little bit later, which is if I know that the molarity is moles per liter, let's say I want to just use milliliters, because they give you stuff in milliliters a lot. So in order to use milliliters as my volume, we can also use millimoles. Okay, so there's going to be a lot of talk of millimoles in chapter 15. So millimoles divided by milliliters is your molarity. And why that helps, it's going to be kind of a shortcut here in a minute. If I rearrange this to solve for millimoles, so molarity times milliliters equals the millimoles, it's going to help us compare some things without having to convert other things, which just makes it shorter and easier to do. So if I wanted to calculate for sodium acetate, if I calculated the millimoles of that, my molarity is 0.5, my milliliters are 50 milliliters. So I have 25 millimoles of sodium acetate. And then if I do the same thing for the acetic acid, my molarity for the acetic acid was 0.25, and then my milliliters of that is 25 milliliters. That gives me millimoles, 6.25 millimoles of acetic acid. Okay, so that's just kind of a side note right now. We'll use that more in a minute. Okay, here it comes. Best equation ever. Why? Because it's a shortcut, and you don't have to do ice tables when you use this equation. You just get to plug in some stuff that you know and figure out the pH of a buffer
Why didn't you show us this last time?
the short way. We can't use it. You can only use it with buffers. It doesn't work in the last unit. Henderson, Hasselbach. Your heroes. Okay, here it is. If you are asked to calculate the pH of a buffer, you cannot use this with anything else except for buffers, Victor. Okay? Buffers only, which means if you don't have significant quantities of the conjugate acid-base partners, then you can't use it. It is equal to pKa, we'll talk about what that is, plus the log of the concentration, the initial concentration of the base over, now that little thing right there represents initial, right? Over the initial concentration of the acid. And that's it. So, that is it. If pH is calculated by taking the negative log of H, how do you think you calculate pKa? Negative log of the Ka value. Okay, so dealing with the above reaction where we had the sodium acetate and the acetic acid, calculating that pH, it equals the negative log of the Ka for acetic acid, 1.8 times 10 to the negative 5, plus the log of the base over the acid. So the conjugate base concentration was 0.33. The acid concentration was 0.083. Go ahead and get out your calculators. Get them out. Calculate this. Answer. It gets even better in just a minute. Even better. Did you get an answer?
Yes.
What did you get? The same. Well, kind of. You actually get 5.34, but that is close enough. And so you don't have to ice table. And you want to hear something that's even better news. Okay, this is already a shortcut because you don't have to use the ice table. The other shortcut is, up here to figure out these concentrations, we had to do M1 V1 equals M2 V2. instead of concentrations here, you can plug in your millimoles, which means that you don't have to calculate M1V1 equals M2V2. All you have to do is take the molarity times the milliliters, get your millimoles here. So this one would be 25, yes. And then this one would be 6.25. And because you end up dividing it by the same total volume and all that stuff, the ratio ends up being the same. So you don't have to even do that step. You can skip that step completely. Do you want to plug it into your calculators, or do you believe me? It is, okay? So it takes out that step. So again, this equation only works with buffers, but it's nice. So I'm going to let you guys have a little fun with this equation here. No, not yet. Oh, okay. We're more than halfway done. No, I have some more stuff. Okay, so calculate the pH of this solution. Okay, I'm going to give you this stuff, and then you're going to calculate it for me. So 25 milliliters of 0.150 HClO. Ka equals 3.5 times 10 to the negative 8. What is HClO? Hypochlorous acid. This was on your test. And some of you got that, and some of you did not. It is weak. It is not strong. Okay, there are also in this year, I'm going to add 32 milliliters of 0.45 molar. Oh, I forgot to do this. 0.45 molar of KClO. And I want you to go through and calculate the pH. Use the Henderson-Hasselbalch equation. You're taking the two solutions are separate to begin with, and you are adding it into one big solution. So you'll need to calculate millimoles of each one instead of doing M1V1 equals M2V2. And then plug stuff into your Henderson-Hasselbalch equation and see what you get for the pH, okay? Do that now. What's wrong? What's that?
But I should have gotten this recently. I don't really know how it goes. Like,
Oh, you can do it.
I don't know the times.
Oh, yeah, they can just come back in here. You guys can sit right I think, would you do That's not curved at all.
Yeah, it's 1.75. I don't know which one to do or what. Did you do? Well, I was just writing.
It's the millimoles of the base over the millimoles of the acid. This is what you should be plugging into your calculator. So to find pKa, negative log of that Ka value. And remember on your equilibrium section of your reference sheet, you guys knew all of these, now you know this is the Henderson-Hasselbalch equation right there. That's given to you on the test, the AP test, your test here. You never have to remember it. You just have to know what it's used for, which is the pH of buffers. And then it also tells you how to find pKa, which is the negative log of Ka. What did you get as an answer for the pH?
Like 7. Almost 7.
8.04. I did not.
How do you know which one goes on top or on the bottom?
The base goes on the top. And so the one that is the conjugate base, which is this one right here, because the potassium crosses out basically, and the acid goes on the bottom. Okay, one more example and then I'll give you a short break. Short though, because I'm not all the way done. I'm just switching gears after this one. The only difference with this is that you're dealing with a buffer that has a basic solution in it instead of an acidic solution. So we had one that had acetic acid and then the acetate ion. Now we've got ammonia as part of the solution, which is basic. So it only changes one thing. So I won't make you redo the entire problem. When you have a buffer solution that has basic stuff in it, then they give you the Kb value. And it just so happens that the Kb value for ammonia is the same as the Ka value for acetic acid, but that's the Kb value. So the only difference here is a couple things. The equation does not change when you're dealing with buffers that have bases in them, like NH3 weak bases. It's still pKa. So that means that you first have to figure out Ka by doing Kw over Kb and then plugging that in and negative logging it. So you still, that's the added step. And then everything else is the same. Now in this case, in this particular problem, they tell you the pH of a solution that is, so it's already a solution altogether where you've got 0.5 molar ammonium chloride and 0.3 molar ammonia. So those are the molar concentrations. And if they give you the molar concentrations of the solution after it's already combined, then you can just plug that in. So for the base, it would be 0.3 molar, and then for the acid, it would be 0.5 molar. And then that would give you a pH of 9.03. Okay, oh, because the Ka value you get is like 5.56 times 10 to the negative 10. So then you negative log that. All right, you have 2 minutes for a break, and then we're going to come back and we're going to talk about what happens when you add acids and bases to buffers. It's kind of a quicker section. There's no actual calculating, but just take a minute to take a break. And if you didn't calculate those numbers, go through and make sure you can figure out how to do that on your calculators. Yeah. Very tired? Yeah. Glad it's Friday? Yeah.
Okay, it's about time. I wish it was summer. Waiting 5 days.
You got a lot to do before summer.
Not really, no.
Oh yeah, if you have your rulers, you can use this time to bring your rulers back.
Are we like halfway through summer from the new year?
Oh yeah, it's almost summer. Sure.
Yeah, the only thing is you have finals and AP tests in the way and in the
otherwise I have to upload it as 2 different videos, and then it's just a big mess. They can skip through this part if they want. Those people that aren't here today. Yes, we hope the robotics team is doing well. Tennis players, they're all gone.
Robotics.
So, would we be able, instead of like doing KA equals KW over KP, we should do 14 minus negative log KB? That just didn't work out.
Oh, yeah.
So will that work every time?
Yes, it should.
Okay.
Yeah. Okay, let's do this. Now we are not going to do any calculations. It used to be that you would have to, like last year, they would have to, after we add an acid or a base to a buffer, they would have to calculate what the new pH was. Okay, we don't have to do that anymore, but you do have to know what reaction happens that makes it so that the pH doesn't change very much. So we're going to go through each situation fairly quickly and take a look at that. So the whole point of buffered solutions is that you can add whatever to them and the pH stays pretty much the same. So we need to see how that happens. If we have a strong base, such as sodium hydroxide, let's add sodium hydroxide to an acidic buffer, which just means that you're starting out with the acetic acid, and they sometimes just show it with like a little slash to show we've got acetic acid and a sodium acetate combination that makes that buffer, because remember the whole definition of a buffer is that you have a weak acid and its conjugate base in significant amounts. And so I've got those things in that buffer, and I'm going to add a sodium hydroxide to it. What you need to do in order to figure out the reaction that takes place is you need to get inside the beaker and figure out what's there, okay? Because we have lots of things happening. And so I'm going to go through, and with each thing separately, I'm going to show what those things look like when they're in an aqueous solution. So, sodium hydroxide is strong, which means that it ionizes into sodium ions and hydroxide ions. So I want to show in the beaker, okay? It's almost impossible to set up these reactions without showing what's happening in the beaker. It's hard to visualize. So I have sodium and hydroxide. Acetic acid is a weak acid, so really it pretty much all stays together. So I'm going to keep it together in the beaker. Sodium acetate, any salt ionizes. So those break apart and ionize. Now, the other thing is that you can cross out ions that don't play a role in the whole situation. Kind of like the ions that you crossed off when we were dealing with the pH of salt solutions. Yeah. Do you just need one?
Yes, please.
I have 2.
Yeah, I just need one. Gotta play Pac-Man.
Okay, so let's see. You need to figure out what reaction takes place. Now, you're always going to start writing the reaction starting with what you added. I added the hydroxide ions. Now, I added sodium hydroxide, but sodium ions don't affect anything, so I'm going to forget that they're there. So start out by writing out the ion that I added, which is hydroxide, and then I need to figure out what it's going to react with here. Now, can I put 2 negatives on the same side of the reaction, do you think? No, they're not going to go on the same side of the reaction. They're not going to react with each other. They can't do anything. And so it can't react with that, so it has to react with the other thing. So it's going to react with the acetic acid molecules, and it's going to make water and acetate ions. Okay, so when I add hydroxide ions to this, my buffered solution takes those hydroxide ions and turns them into water and acetate ions, which doesn't affect the pH nearly as much as hydroxide ions do by themselves. So a couple things you have to remember. Partners need to be on opposite sides of the reaction, so never put them on the same side. And then you start with what's being added, and what else? Oh, the same charges. So similar charges on opposite sides. So if you can remember those rules, then you should be able to set up the reaction and what takes place. All right. Now let's add a strong acid, HCl, to a buffer that's made with a weak acid, HFNAF buffer. Draw your beaker. And let's think about what happens in the beaker. Hydrochloric acid ionizes strong acid. HF stays together. Sodium fluoride ionizes. What ions can I cross out from the beaker here? What doesn't affect the pH or anything at all? Sodium chloride. Sodium and chloride ions. I'm left with those. They're the same ions that you can cross out, by the way, just like we crossed out from chapter 14. I'm going to start with what I added. I added HCl, so I added hydrogen ions. What do you think it's going to react with, and what do you think the product is going to be? It's going to react with the fluoride ions that are already there because I had that sodium fluoride dissolved in solution, and it's going to make HF. So I add a strong acid. The presence of the common anion reacts with it, forms a weak acid, doesn't change the pH very much. Okay? Next. If I add an acid like HCl to a buffer that's made with a weak base, NH3, and then ammonium chloride, in the beaker, I have hydrogen ions, chloride ions from the HCl. NH3 is a weak base, and so it doesn't ionize, stays like that. Ammonium chloride ionizes, it's a salt, so I have NH4 plus ions. I've got chloride ions. Chloride ions cancel. And if I write out that reaction, I start with what I added first. So I start with my hydrogen ions. Whatever you added to the buffer always has to be part of the reactants in the equation. So hydrogen has to be one of the reactants. The other thing here, if you just kind of look at what you have, I can't have hydrogen and NH4 together on the same side. I can't have those on the same side because they're partners. So I have to have hydrogen plus NH3 gives me NH4. So it takes those hydrogen ions, which would make it acidic normally, and turns it into NH4 plus, which is weak, and so the pH is not affected. Okay, last thing, very last thing. Adding a strong base like sodium hydroxide to a basic buffer. This is kind of the more common one. You've got NH3, NH4Cl. In the beaker, sodium hydroxide ionizes, strong base. NH3 stays together. NH4Cl ionizes. I can cross out sodium. I can cross out chloride ions. I start with what I added, which was OH ions, hydroxide ions. NH4 and NH3 can't go on the same side. They have to go on opposite sides. So I have to figure out which one of those two the hydroxide is going to react with. Is it going to react with the ion or with the ammonia? The ion, right? So OH plus NH4 plus is going to make water and NH3. So it takes strong basic hydroxide ions, the buffered solution, turns it into water, and a weak base, so the pH is not affected very much. So you need to know kind of everything that goes on there and be able to write out those equations. So just show everything in the beaker and then you can figure it out a little bit easier.